When working with sequences of numbers, we have different kinds of formulas to describe those sequences. One kind of formula is a recursive formula. A recursive formula tells us two things. First, it tells us the starting number. And then it also tells us the pattern that we need to keep repeating to get the next number in the sequence. Here's an example of a recursive formula. Notice it has two parts. This first part tells us what the sequence starts with. The first term is 22. The second part tells us the pattern that we keep repeating. So a sub n, that's the term that we want. That will equal the term right before the term we want plus 9. So in other words, we just keep adding 9. So this sequence is 22, we add 9. Then we keep adding 9. So we found the first 5 terms of this sequence. Now don't let the notation intimidate you. The subscripts just tell us what term number we're talking about. So a sub 1, that's just the first term. So notice we started with 22. A sub n, that's just whatever term in the sequence we're interested in getting. And a sub n minus 1, that's the term right before the one that we want. So this just says to get the term we want, we look at the term before the one we want and add 9. This particular sequence is an arithmetic sequence because we are repeatedly adding the same number over and over again. Here's an example of a recursive formula for a geometric sequence. All right, the first term is 3, so the sequence starts with the number 3. And then to get the term we want, we take the term right before the one we want and multiply by negative 3. So we're going to repeatedly multiply by negative 3 to create the sequence. So we start with the number 3 because they told us what the first term is, and then we're going to multiply by negative 3. Negative times negative is positive, so notice when we're multiplying by a negative number, the sign keeps switching. Let's take a moment to compare recursive and explicit formulas. They tell us two different things. Recursive formulas, once again, have two parts. They tell us the first term, what the sequence starts with, and then they tell us the pattern we're repeating. So in this case, we keep subtracting 50 to create the sequence. Now over here, we have an explicit formula for that same exact sequence. It will have the same starting number, and it will have the same pattern. But this rule looks different. There's only one part to it, and it just says to get the term we want, we plug in the term number, multiply by negative 50, and add 64. And that will tell us a specific term number. So if we wanted to find like the 100th term in the sequence of numbers, that would be much easier to figure out with an explicit rule. We just plug in 100 on the right side of the formula and work out the math. Because the recursive rule just tells us what we start with and then what we keep doing to get the next term. So to get the 100th term, we would have to start at the beginning and write the first 100 terms of the sequence. Okay, let's practice writing recursive formulas. So remember, the formula will have two parts. We identify the first term, so in this case it's 15. And then we indicate what the pattern is that we're going to repeat. So the term we want will equal the term right before the term we want. That would be a sub n minus 1, the term right before the one we want. And let's see what we need to keep repeating. So in this case, we are adding 7 each time. So we just write plus 7. So one advantage of a recursive formula is we can pretty much write the rule or the formula just by looking at the sequence. Let's write a recursive formula for this geometric sequence. All right, don't forget your recursive formulas always have to have two parts. We have to identify the first term. And the second part is where we identify the pattern that we're going to keep repeating. So we're going to take the term right before the one we want, and we're going to multiply it by, we'll notice in this case that we are multiplying by -4 each time. We see that the sign is switching because a negative times a negative is a positive, and then a positive times a negative goes back to negative. So to get the term we want, we'll take the term right before the one we want and multiply by -4. And there we have our two parts to our recursive formula. All right, here we have a question that highlights the limitations of a recursive formula. We need to find the 50-second term. All right, so we have our sequence. It starts with a -39, and then we keep adding 7. So to get the term we want, we look at the term right before the one we want and add 7. So to get the second term, we're going to look at the first term and add 7. To get the third term, we're going to look at the second term and add 7. Now we could keep on adding 7 until we get to the 50-second term. But if we remember how to write an explicit rule or an explicit formula for this sequence, we'll be able to figure out the 50-second term much quicker. All right, so this is an arithmetic sequence since we're just repeatedly adding 7. That's going to be our rate of change. So for our explicit formula, well, the term we want, that's going to equal 7 times the term number. And then to get our adjustment, because we want this formula to start with -39, and if we plug in 1, 7 times 1 is 7, so that's not going to work. Well, we can take a moment to imagine what the term before -39 would be if there was a 0 term in this sequence. And that would be -46, because -46 plus 7 equals -39. So that's our adjustment right there. Now, -46 is not a number in this sequence, so we'll go ahead and get rid of that. And let's check our sequence, make sure it works. So if we plug in 3 into this explicit formula, we should get -25, because -25 is the third term. So 7 times 3 is 21, and 21 minus 46 does equal -25. So this formula does seem to work. And now we can figure out the 50-second term. So the 50-second term, or a sub 52, will equal 7 times 52 minus 46. Working that out on a calculator, we get 318. So in this case, instead of extending the sequence all the way out to the 50-second term, we looked at the first few terms, wrote an explicit formula, and used that to figure out the 50-second term. I hope these examples have been helpful. This is Mr. Ela, signing off.